In this session, we are going to study simply supported beam with point load. And suppose let us take the simple case that the point load is at the center. So this is our simply supported beam, which is hinge at one point and roller at the other point, right? And there is a point load, suppose at the center, W. The length of this beam is L. In simply supported beam, we have always to find out the reactions at the supports, right? Because whether we will take the left side or right side, the reaction will come into picture. In cantilever, this was not the case. If we are taking fixed point, then there was reaction. At free end, there was no reaction. So that's why it is better to take the free end in cantilever beam. But here, whatever case you will take, whether to the left or right, there will be a reaction. So first we have to find out the reaction at A and at B, right? So how to find out the reaction? For finding the reaction, you can take moment about any point. Suppose taking moment about a point A. So take moment, and suppose let us have a reaction. You can choose any direction. Suppose this direction, because force is downward, so reaction may be upward. Whatever reaction direction you can choose upward or downward direction. So RA is the upward, suppose, and also suppose that RB is also upward, right? So we are assuming that both the reactions are upward. RA and RB are the reactions, and there will be no horizontal reaction because the load is only vertical. If there would have been a incline or horizontal load, then there should be a horizontal reaction, but here only vertical reactions will be there, right? So we have to find out RA and RB. Two unknowns are there. So take moment about A. We have to take the moment about A. So moment of all the forces should be 0 about hinge point. So RA multiplied by, because there is no moment, RA is passing through A, so it is of no meaning. So moment of RA will be 0. Moment of W, so let us take clockwise positive and anti-clockwise negative. So W multiplied by the length, this distance is L by 2, because it is at L by 2 distance from the center, right? So W multiplied by L by 2. So W multiplied by L by 2. This is clockwise, this is anti-clockwise. So RB multiplied by L. So minus RB multiplied by L, and that should be equal to 0. All the moments about point A should be equal to 0. So all the moments, so sum of the moments about point A should be equal to 0. So from here you can find out RB, and you will get RB as W by 2. So this is the one of the reaction we have find out, that RB will equal to W by 2. So this RB is W by 2, right? Now we want to find out RA. We know that sum of the forces in downward and upward direction should be equal. So W plus minus RA minus RB should be equal to 0. This is another case. So we can also take that sum of all vertical forces should be equal to 0. So we can take downward forces as positive, so W, upward forces as negative, minus RA minus RB should be equal to 0. And what is RB? That is W by 2. So from here you can write W minus RA minus W by 2 should be equal to 0, and from here we can find out RA as W by 2. So half is a load taken by the hinge, and half with the load will be taken by the roller joint, right? So RA is also W by 2. So RA is equal to W by 2. So RA is W by 2, RB is W by 2. Both are W by 2. And we want to draw the shear force and bending moment diagram. Now we can find out the reaction at certain point. You can choose any direction. left or right, it depends upon you. So let us take the, suppose we are taking x at this point, suppose from point end A. Whether you can take from B also, but I am taking from here. Suppose this is x, and we have to find out the shear force at this cross section, suppose capital X. So shear force will be the algebraic sum of all the forces to the left of this section. There is only one force to the left of this section, that is reaction, W by 2. But this is valid from A to, suppose this is C point. This is valid only for A to C. When we cross this C, here there is a load. So the equation will change. So we have to take 2 times the cross section, one for A to C and another for C to B. So one we are taking x at a distance x, we are taking cross section x, right? And we have to find out the shear force at point x, right? So shear force, for making shear force diagram, what we can do is we can find out the forces at x, and that will be equal to algebraic sum of all the forces to the left of this section, because we are taking section here from left. So we have to take the to the left of this section, and there is only one force, and that is upward. So left upward. So left forward is this, left upward, and this is positive. So this W by 2 is positive, right? So Fx will be equal to W by 2. W by 2. And this will be valid between A to C. A to C, and this is positive, right? So let us side by side draw the shear force diagram also. This is our base AB, this is our beam, and this is positive W by 2. W by 2 is positive here, W by 2, and it is valid from A to C. It is valid from A to C, right? So this is W by 2. W by 2 from A to C, right? So this is the case, and this is positive in this part, right? So just before C, we have made this diagram, right? Now what is happening from C to B? This equation is not valid. This equation is not valid because the force is changing now. There is a force W here in between. So we have to take another section. So let us take another section here, and suppose this is, let us name it x1, and the cross section name is capital X1. So at a distance from A, at a distance x1, we are taking a cross section capital X1, and we have to find out the shear force at this x1. So what is the shear force at Fx1? And that will be equal to algebraic sum of all the forces to the left of the section. And to the left of the section there are two forces. One is this reaction W by 2, another is capital W. So this W by 2 is positive, leftward positive, so this is W by 2, and capital W is negative because this is downward, so this will be minus W. So this will be minus W by 2. So this will be minus W by 2, and it is valid between C to B. So at just at point C, there is abrupt change from positive W by 2 to negative W by 2, right? So it is constant from C to B. So there is a abrupt change, right? So just at the left of C, the force is W by 2, and just at the right of C, the force is minus W by 2. These are the shear forces. So there is abrupt change. There is abrupt change from positive W by 2 to negative W by 2 here, right? So this was positive W by 2, and here it is minus W by 2, negative side here it is, right? And it is constant from C to B because there is no other force here. So this is constant from C to B, right? Like this. So this is negative here. And at B, this is W by 2, right? So at A, at B, all the forces are W by 2. So by this you can find out the shear force diagram. So the shear force diagram is W by 2 from A to C and minus W by 2 from C to B, and this is our point C, right? So this is the shear force diagram. Now bending moment diagram. Similarly, we can take two cross sections, one between A to C and another from C to B, and we can take x distance at a cross section x and x1 distance at a cross section x1, right? So bending moment will be the moment of this W by 2 about this x. So this is W by 2 multiplied by x. So this will be the moment. So mx will be equal to W by 2 multiplied by x. So this will be W by 2 multiplied by x, and this is valid between A to C. So this is for A to C, valid for A to C, and whether it is negative or positive, this is leftward, upward, clockwise. So leftward, clockwise is positive. So this is sagging bending moment, right? So this is positive. And what is the value at A? If we take the endpoints A and C, so what is MA? That is 0 because x is 0. And what is MC? That is L by 2. Length is L by 2 at C. So this will be ML by WL by 4. So this is WL by 4. And both positive. Right? Now this is valid between this to this, right? So we can draw now bending moment diagram like this. We can take a line from 0 at A to some value WL by 4 at point C, and this is a straight line WX by 2, straight line. So draw a straight line from here to here like this. So this is the bending moment diagram between A to C. Now from C to B, we want to draw from C to B. What is happening from C to B? So from C to B, we will take this cross section as reference, x1, which is at a distance of small x1, right? So mx1 will be equal to there are two forces now. One is W by 2 and another is W. So W by 2 is at a distance x1 and this capital W is at a distance L by 2 x1 minus L by 2, this distance only, this distance. So this distance is Cx1 is x1 minus L by 2, right? So the moment of W by 2 will be positive. So W by 2 multiplied by x1 minus moment of capital W will be, that is x1 minus L by 2. So that will be x1 minus L by 2, right? So how much will it come? This will again come Wx1 by 2. This should come that Wx1 by 2. So how much it will come? This is Wx1 minus plus WL by 2. So this is WL by 2 and Wx1 by 2, this, so minus Wx1 by 2, right? So this is the bending moment at a cross section x1, right? So this is WL by 2 minus Wx1 by 2, right? Now this is the bending moment. Now, what is bending moment at endpoints? And this is valid between C to B. This is valid between C to B. So what is the value at C? At C, x1 will be L by 2. At C, x1 is L by 2. So put x1 is equal to L by 2, you will get the bending moment at C. And that will be equal to, bending moment at C will be equal to, again, WL by 4. We have already found out the bending moment at 4 is WL by 4. So you can put here L by 2 and you will get the bending moment as WL by 4 at C. And bending moment at B, MB will be equal to, at B the x1 will be L. So you will put L and that will cancel out, that will be 0. So from WL by 4 to 0. So WL by 4, it is already WL by 4. From WL by 4 to 0, this is our bending moment diagram, right? So this is our bending moment diagram for this case. Is it okay? So this point is, this distance is WL by 4, right, on a scale. And at A and B, the bending moment is 0. So you can see here, the bending moment is not changing at this point. It is just changing the curve, but due to this point load, there is abrupt change in shear force, but there is no abrupt change, there is no change in bending moment. WL by 4 was there for AB, AC and for also for CB. So you can see here, there is no abrupt change in bending moment, but there is abrupt change in shear force. So this is our shear force diagram and this is the bending moment diagram. So this is how you will find out the shear force and bending moment diagram of a simply supported beam with point load, and this is positive.